A postdoc at Berkeley, although I've actually started my academic career in the department that's over there, so it's been very nice to kind of be back in Cambridge looking around. So I've just introduced some of my collaborators up here. The two kind of main people are Martin Bazan, who is a professor in maths at MIT, and Ken Cameron, who is another graduate student. So a lot of the first half of this talk was done in collaboration with them when I was there as a graduate student. So I want to kind of talk today about a kind of a very interesting kind of aspect of dense granular flows. I'm very interested specifically in industrial problems where you would have to deal with mixing in granular flows, where you're not just kind of concerned about kind of mean flow properties, but you really care about microscopic statistics. And I just want to kind of give an example of something that I worked on, was this model for a pebble bed nuclear reactor. So this is a kind of prototype design for a reactor that would feature like a large container full of two types of pebbles. The light-colored ones would be fuel pebbles that would contain like uranium ore, and then the dark-colored pebbles would be kind of moderator pebbles. And during this thing will basically cycle very slowly, and you're really interested in kind of a lot of the kind of key questions in this situation are microscopic. For example, you're really interested in how this interface between the two will behave. That's kind of critical in terms of the reactor performance. You're also interested in things like porosity, like what will the packing structure be like? How will that affect gas flow? Because this reactor works by pumping helium up to kind of extract out the energy, and obviously porosity will affect that. And to do this simulation study was done using discrete element simulation, which was extremely time consuming for such a large situation. And it really kind of begs the question, well, suppose you're in a situation where you want to kind of find out some of these microscopic statistics, but you want to do it rapidly. You want to do it in like a situation for real-time control, or you want to kind of do it in a situation where you might want to run many tests and to optimize something. Then what could you do? So this is like a real problem. I mean, to an audience like this, I don't need to kind of go into details about the problems of kind of modeling materials microscopically. Yeah.
The previous slide.
Yeah.
Can you just describe what is the white color and blue color and what is you are simulating?
So the white color is these fuel pebbles. So they're basically like 6 centimeter diameter pebbles which contain uranium ore, and then the dark color is these moderator pebbles, which is same 6 centimeters in diameter, but are used to kind of moderate the nuclear reaction.
Shouldn't they be mixed?
Actually, it's for this type of reactor design, you actually want that interface to be as sharp as possible. If there is mixing there, then that can actually kind of be detrimental to the reactor performance.
Okay, carry on.
So this is, suppose I mean, one thing you might want to say is, well, could we apply like a continuum model? But obviously, like there's there's very kind of difficult questions with that. Like we know that like at the micro scale, we have things like force chains. I mean, how can we even define continuum quantities at that level? But at the same time, there are situations where we can kind of see smooth flow fields developing. And I just want to kind of, on the right here, this is an image from Clark University of granular drainage between two parallel plates of different colors of sand. And you can see this kind of very nice kind of smooth flow profile developing. And some of these profiles, for this kind of profile, you can see this kind of quadratic, this kind of parabolic shape of parabolic flow region. And you can think, well, that's something that kind of suggests perhaps some kind of diffusive process, like something where we can think of something diffusing from that orifice. So to get started on kind of coming up with a microscopic model, we can kind of go back to the basic physics. And one thing that's kind of been widely reported in literature is this idea of spatial velocity correlations. Like if you look locally, like at how one particle's velocity is correlated with its nearby neighbors, then you often see like a decaying correlation on some kind of mesoscopic scale, kind of typically on the order of like kind of 3 to 5 particle diameters. And what that's basically saying is that you can kind of think of particles moving like this as a group. Like a single particle can't move by itself because it's too geometrically constrained by its neighbors. It would have to kind of flow in some kind of cooperative fashion with its neighbors. So my previous advisor kind of came up with this idea that we can introduce some object, which he called a spot, which is kind of shown by this blue circle, that would kind of move through a flow, and it would cause these correlated motions to occur. So the idea is that this thing could move upwards, as shown by the blue arrow, and it would cause like a correlated motion of particles in the opposite way. Now, that model by itself was kind of enough to get some kind of basic, to do some basic mathematical analysis. But you can kind of take it a step further, and you can say that, well, after you applied something like this, then you could also kind of roughly enforce geometrical packing constraints by applying some kind of elastic relaxation, so that if particles get overlapped by that basic bulk motion, then we can kind of fix geometrical constraints. So that would basically give you like some kind of model where you could imagine you would have some kind of local cooperative motion that had some corrections to kind of make it geometrically valid. Now, it's not clear whether you could kind of use that as the basis of a simulation to create realistic packings. So what we did was we actually carried out a comparison to a discrete element simulation in a rectangular hopper. It's things like 50 particles wide, 8 thick, and about 110 high. And on the left, this is just a discrete element simulation. And we tried to recreate this using kind of the spot model approach, where we'd introduce these spots at the orifice, and then they would diffuse upwards according to a random walk. Now, because there's no detailed force model in this, it can run like a lot quicker than a discrete element simulation. This thing would run in parallel on many processors. This thing can run a single processor in a much shorter amount of time. I'm just going to show like what happens during flow. I mean, we don't get things like perfectly right, but we can kind of get a reasonably good match to like the overall characteristics of like how particles would move. We can, in this paper, we actually did like a quantitative analysis looking at like how well could we match these things quantitatively, and we get a reasonably good match for many things. We were very kind of excited that we could actually kind of track changes in like the radial distribution function, so we could get a reasonably accurate packing over the lifetime of the flow.
Where are the spots?
So I'm not showing them, but they're just kind of diffusing up through the packing. So a consulting company actually saw this work, and they actually were consulting for a coal power plant in Ohio. And this was actually a situation where they had a problem, like a kind of real problem like this. They have like large kind of hoppers where they store the coal prior to using it, and they kind of take deliveries of coal at the top that kind of come in as layers, and then they have several different orifices, and they want to know what's going to come out as a function of what will go in. They thought about using the discrete element method, but it was too kind of time consuming for like this kind of real-time process. So they actually kind of adapted the spot model to kind of create a kind of a ballpark estimate of mixing. Now, there are problems with this model, and one thing that we did was to kind of actually look at like what does the spot model say about kind of small changes in packing fraction, which are often like a kind of a key signature of flow. So one thing that I used was like a local Voronoi tessellation to look at kind of very small changes in packing fraction, and kind of we see decreases from kind of around 5% during flow. You can see like a kind of key difference here between like the discrete element method where your kind of dilation is concentrated in areas of high shear, and in the spot model where your dilation is in the areas of highest flow. So that's something where that was kind of just like one example where you could see like some difference. That was actually done using a 3D Voronoi tessellation, and I've actually developed like a 3D library to do kind of cell-based Voronoi tessellations to apply to like very large systems. And if anybody's interested in that, then then ask me later. So suppose we want to generalize this basic idea of kind of mesoscopic motion and apply it to like any kind of granular flow. Well, to do that, we really kind of need to go back to the physics and kind of start doing some continuum modeling. So now we can't accurately define kind of continuum quantities on the scale of a single particle, but we could potentially do them on this kind of local mesoscale. So this is kind of like a separate study that we did where we were looking at continuum quantities approximately on this local scale. So this is the basic recipe that we'd follow. We kind of calculate like continuum quantities of interest on this local scale, and then we'd view all of those kind of little elements as like a big kind of ensemble, and then we'd like look for statistical signatures between typical kind of continuum quantities of interest, like the Moore Coulomb yield parameter, like which is like the ratio of shear stress to normal stress. Also things like strain rate and total strain. So this is an example showing 3 of these quantities in a granular drainage experiment. Showing on the left this mu, and in the middle packing fraction, on the right the magnitude of strain rate, and we can start to see kind of correlations between the variables like packing fraction and strain rate are reasonably correlated. The correlation with mu is less clear. We can also do that in kind of other experiments. This is the same quantities in a wide silo, and then on the right I'm showing these quantities in a pushing experiment. So what happens is that the right half of the base is pushed up at constant velocity, and that creates like a deformation region. So now what I can do is I can take all of those points and basically view them as like one big ensemble, and I can start to look for kind of like for relations between them. So each of these points in this diagram is basically an instantaneous measurement of kind of normalized strain rate against packing fraction, and we can kind of see approximately kind of a verification of shear dilation. Now we have kind of sacrificed by kind of doing it on a mesoscale. We've sacrificed kind of fidelity. We can't kind of see things very accurately, but we can kind of, this does give you a verification of kind of continuum postulates at the local level. Now we can kind of go further, and we can actually look at like histories. So what we can do is we can introduce like a bunch of traces in the flow that are advected with the continuum field, and for each one of those we can kind of construct a history of these kind of continuum parameters of interest. So what this is showing you is a plot. Each one of these traces is a plot in the phase space of mu against packing fraction. We can kind of see the role they would play in failure. Basically, we can see that like a large number of these traces would kind of increase up to some kind of critical value of mu around 0.55, and then kind of start to move leftwards and dilate and fail. Another thing we can do is we can also look at shear dilation more carefully. There's kind of some debate in the literature, some models that are based on kind of total strain of a material, other ones which are based on kind of strain rate. And this one thing that's very useful in this is a shearing experiment, kind of where we would move the walls on one side inward, the walls on another side outward. And one thing which is very good about that is that then each element experiences a constant strain rate, because the flow is perfectly into the flow is kind of aligned in this direction. So on the left here, you can kind of see, if you plot traces of strain against packing fraction, you can see that the traces basically kind of all align, showing you that strain is somehow involved in the kind of the failure process. But if we plot against strain rate, we can kind of see that the final points will basically align, and we can kind of figure out that strain rate might be kind of involved in kind of like the final state. Another thing we can do is we can kind of directly test the coaxiality. So what I'm showing here is these little crosses are the purple and blue ones are the eigenvectors of the stress tensor, and the orange ones are the eigenvectors of the strain rate tensor. And what we can see is this is using instantaneous data on a 5D scale. And you can kind of see this reasonable kind of approximate agreement, even using instantaneous data. So I mean, and you need to kind of bear in mind that this is still consistent with this idea of force chains, but kind of in this kind of 3D setting where you would where these force chains are maybe not quite so significant as in 2D situations, and where you're averaging out over a fairly small region, you can kind of make some sense in a continuum way. So now, for the final part, I just want to kind of take these two ideas, take this idea of like the spot model, which gives like a kind of mechanism for kind of moving particles locally, and also take, and then we've also just shown that kind of it might make sense to kind of apply a continuum approach down to some mesoscale. So can we combine those to kind of create just like a general simulation technique for simulating kind of microscopic features of flow? So this is kind of like a kind of a proposition for a model where you would have like two parts. One part you would have a continuum model where you would carry out a continuum on some kind of local length scale, like the correlation length scale. And for each of those continuum grid points, you would have stress, you would have velocity, and to kind of track the edge of the packing, you could make use of like the level set technique, which is like used to track interfaces. Now, what I want to do is I want to carry out like an elastoplastic model, and I want to for this situation I'm going to try and keep it as simple as possible. So I want to use. And what I'm going to do is I'm just going to put in two ingredients, which I basically got from my previous continuum results. So one is that I can have a plastic yield, which is controlled by this more Coulomb parameter mu, and using my previous results, I can kind of come up with a functional form for that yield. And I can also have a term for shear dilation based on the results for strain and strain rate. So that would basically give you a model something like this. So these are kind of the two key terms that I've put in from kind of my previous results. Like here is kind of my failure term, and here is my shear dilation term to kind of match previous results. And these two functions, like mu c and phi s, are basically kind of set from my kind of previous results. So now I can then use that continuum model to kind of drive a discrete model. So if on top of having my continuum representation, I can have a representation of my particles themselves. And if I want to move them, then I can first apply a continuum velocity field, which is interpolated from my continuum model. Now then that's obviously going to not preserve packing constraints. So then after that, I can apply a local relaxation. After I've applied a continuum, I can then locally kind of geometrically enforce packing constraints. And I can also even kind of feed that information back in. So if my continuum field goes this way, my relaxation points upwards, then I can update my continuum velocity to what it should have been. So this basically gives you a kind of a basis for a multiscale simulation technique. So on the left here, I'm showing kind of two discrete element simulations. So this is one that I showed before, like the packing fraction in this pushing simulation. And then in the bottom corner here, I'm showing the shearing simulation, where the walls are kind of shearing into and out of the display. So this is kind of like a pretty time-consuming simulation. And then using this multiscale idea, I can kind of basically kind of do the same kind of idea, and I can get like a reasonable kind of match to the continuum flow, and I'm also kind of moving particles in roughly the right direction. So and this is kind of a very small fraction of the computational cost of full DEM. So now there's obviously a lot of things that could be improved here. I mean, there's a lot of things you could do in terms of making a more realistic continuum model. And there's also ways in which you could improve that discrete step. So one potential way that you could improve the discrete step is kind of bringing in more kind of basic physics. So this is an example of a project I've been doing with Gary Grest at Sandia, like doing kind of large-scale simulations of granular flow in a cone. So one thing you can do in this is you can apply a similar kind of technique, and you can calculate strain rate tensors and also like a granular temperature tensor on like a local scale, like on this kind of in basically like 5D boxes. Now we can actually see a reasonable agreement between the kind of the strain rate tensor and the temperature tensor. One thing that's maybe not totally clear from this is that you often see that the temperature tensor is skewed towards the vertical direction, which I think is kind of some signature of gravity. Basically, the particles can only fall in that direction. But you could think that, well, if I have some kind of idea of how temperature could behave in this, then I could use that to kind of make a more realistic discrete step. So rather than just kind of moving particles according to the continuum field, I could also build in like a stochastic term to kind of mimic the temperature that you might see. So anyway, that's kind of work in progress. So I'm just going to finish with my conclusions. So this is basically like a kind of taking a discrete problem, like a discrete study and a kind of continuum study, and kind of combining them into some kind of multiscale approach. So this could potentially be used as like a rapid technique for simulating mixing in kind of engineering problems, but it could also be something like a kind of a general framework for kind of looking at kind of stochastic effects in dense flows. So I have kind of a website for more information. I also mentioned that this Voronoi library that I developed, so the web address is there. Yep.
I missed how the spots diffuse.
So they follow, so I kind of have to gloss over that, but they actually follow like a random walk process. So this was originally,
There must be a rate associated with
yeah, so there's several parameters which we calibrated. So you have things like how fast the spots will move. You have things like how much influence they'll carry, like how wide they are.
Is there any feedback to the flow? In other words, you look for chunks of the flow that move with nearly the same velocity, call it a spot, or when you move the spot, does everything suddenly start moving with the same velocity?
So the spots basically, like kind of, they move basically passively through I mean, they're basically objects which move through the flow, and then they cause the flow to move, basically. So they kind of diffuse upwards and then cause the particles to move.
Now, most of the examples you were showing were kind of quasi-static.
Right.
Can this approach work, and do these models work on faster flows? Have you looked at those at all, or just?
I'm mainly interested in this kind of regime, basically. I mean, I think that you could apply like a more like for the continuum model. You could maybe kind of, if you really thought about that, you could maybe kind of, you could make sure that it would give you a reasonable description at higher flow rates, maybe.
So I mean, how is the strain rate non-dimensionalized when you are plotting the packing fraction against the strain rate?
That's done in kind of the standard way that
With
like using the square root of
Okay.
pressure.
How did you define a spot? I'm sorry, and has it got necessary to be spherical?
No, it's basically just like it's like an object on like a scale of, I mean, in this situation it is spherical. It's an object on some kind of mesoscale. It has some diameter.
And
like
so it tells you which particle you include in what. How do you define a spot?
So yeah, so it's basically you have some length scale to it, and that length scale is basically calibrated from velocity correlations, basically. So I began by talking about velocity correlations.
Yes,
That gives you a length scale, so
And-
you can then use that for the
And
length
is it
scale. of the
obvious
spot.
then the spot moves backwards with respect to the particles in your picture. I don't
Yeah, well, so that's not obvious, but the thing is that this was based on, the original idea from this came from some previous work on something called a void model. It's like something that was proposed in like the 60s, where you would imagine that particles were on a lattice, and then you would introduce voids of empty space, and they would propagate upwards. And you kind of think of them as almost like carrying inverse volume, and they kind of cause particles to move almost like a sliding puzzle. So this was almost originally kind of conceived as like a generalization of that. So you kind of think of them like particles flow out of the orifice, and spots basically carry like a negative volume, and so you can kind of introduce them at the opposite rate.
like a bubble.
Yeah, basically.
Yes, I know there are lots more questions, but I think we have to move on, and I encourage you to have discussions afterwards.